Hello, everyone. Welcome to the SZ4Grads Spring Webinar Series. My name is Hagor from the University of Wisconsin-Madison. I'm today's webinar's host. This webinar is organized by SZ4D and SZ4Grads. So first, I would like to briefly introduce them. SZ4D stands for Subduction Zones in 4 Dimensions, which is a community-driven initiative for a long-term interdisciplinary research program to understand the limits and possibilities of geohazard prediction in subduction zones. So SZ4Grads stands for Subduction Zones for graduate students and recent graduates, and is a network within SZ4D for early career researchers studying subduction zone processes. Before I introduce today's speaker, there are several things I want to mention. So first, we hope you can fill in a survey during or after the talk to provide us some feedbacks about this webinar. So let me copy and paste the link to the chat. Sorry, I hope everyone can see the link. The second thing is I want to remind that the live translated captions are available. So please feel free to turn on this option if you need. And also this webinar is being recorded. The recording will be posted on SZ4D YouTube channel. All right, let's move on to today's talk. It's my honor to introduce today's speaker, Yurong Zhang. So Yurong is currently a PhD candidate in seismology at Michigan State University. She earned her bachelor's degree in geophysics from the University of Science and Technology of China in 2020, and has been a graduate student at Michigan State University since 2020. Her research is focused on seismic attenuation studies in the Tonga and South American subduction zones. So okay, let's welcome Yurong for today's talk. The title of the talk is P-wave attenuation structure and melting processes of the Tonga-Lau Mantle Wedge. So Yurong, it's your turn.
Thank you so much, Ha, for the introduction. I am actually also another host of this webinar. Yeah, I feel so honored to be one of the speakers during this series. I'm going to share my screen. Can you see it right now?
Yes. Can you do the full screen mode?
Looks good.
Yes. Looks good.
Okay. So first, my title is P-wave attenuation structure and melting processes of the Tonga-Lau Mantle Wedge. This is my first time giving such a long presentation. I feel like I am in a committee meeting. So yeah, I am a little bit nervous, but whenever you have question, be sure to ask it. I will answer it whenever I am available. I really appreciate everybody's patience. This is actually also my first project. Although the title is like more related to attenuation structure and the melting processes, we spent most of the time on the technical part. I'm not going to talk about a lot about the codes we are using, but you are very welcome to talk with me about the technical details. So to get the attenuation structure, we have basically 2 steps. I'm going to introduce it step by step. Here, I thank Sean Wei for being my advisor. He's such a nice person that guides me through academics. And thank you, Joe and Max, for building up the draft for body wave attenuation using 3D Markov chain multicolor method. This is like the basis of my research. And thank Dongdong for providing a lot of nice source parameter data set for me. And thank Fan for contributing to the proposed new velocity structure to this study. So yeah, it all started from plate tectonics. Everybody knows about plate tectonics. Everybody will feel like, speaking of tomography, we think velocity is more familiar than like attenuation. But now I feel proud. I'm going to praise attenuation because the first time people learned about plate tectonics is by using attenuation study in Tonga. So how did they find it? At that time, they have limited stations and limited earthquakes. If we only look at this earthquake here, from now we know this dash line, this dash curve is like the subducting slab, which is very cold. But at that time, people don't know. People think everything is homogeneous in the earth. But actually, the two stations VUN and NIU are at around the same distance to the event. However, the signals they received are totally different. The left one is like only low frequency signal. For the right one, they also have high frequency signal. Anyway, by looking at these two signals, we don't think they are the same. This is because the right signal contains high frequency segment, while the left doesn't. The problem is people think the right portion is like a little bit cold that could let the high frequency go through. Then this is a time they find a cold slab. And this is a start of the plate tectonics. This is amazing. So this picture, this is actually from Wikipedia. It describes a faux image of the plate tectonics we know about today. The subducting lithosphere, the subducting oceanic lithosphere is subducting from the west to the east. As it subducts, the dehydration from the slab could go upwards and cause a partial melting, and probably there is arc on top of it. And also, there are very important structures here in the back arc on the overriding plate, like right on top of the dehydration part, we get the arc. On the arc, the very important topic we want to talk about is magmatism. In the segment between the arc and the trench will be forearc. This is like always known as a could nose. It's also known as its sufficient hydration, but there are also some debate about it. Somebody used dynamic modeling and suggests that this is a dry cold forearc mantle. This is also a very interesting area people want to discuss. Talking about another region, starting from the arc to the region that's far away from the trench, this is called back arc. Sometimes there are back arc spreading centers. This is where we can see the formation of new crust. This is also very interesting. So yeah, Mantle Wedge is a very special place that contains a lot of sufficient information. We want to know about the mantle flow patterns, temperature structure, melt production, mechanics, and the depth extent. Also, we want to know about the melt, water transport, and mechanics. It's a lot. There's a lot to explore. People do geochemistry who are doing like geodynamic modeling, and also seismology. Particularly for us, we're doing seismic tomography. We are all very interested about the Mantle Wedge. So now I'm going to talk about the introduction first. I will start from the very unique Tonga subduction zone, and then I will give you an overview of what is seismic attenuation. What can we do with seismic attenuation other than besides the finding of plate tectonics? And then for the path average attenuation and 3D attenuation inversion, this is how we can find the final attenuation tomography results of the study area. So these are like 2 steps that we want to do to get the final results. And also, I have a ton of future plan regarding this project. Starting from a very simple figure here, this is the Pacific Ring. Tonga subduction zone is at the south of the Pacific Ring. It's in the southern hemisphere near the New Zealand, Tonga, Australia. So this is another cartoon from my advisor, Zhang. Again, if we take a closer look at this subduction zone, this is interesting subduction zone because the plate boundary, the trench here, is an oceanic convergent boundary. The reason of this is because the right part, the Tonga subduction zone, is much older and is much colder, so that it's heavier than it's subducting beneath the overriding Australian plate. However, the overriding Australian plate is also oceanic plate on like in the subduction zone part. It's very easy to be broken. This is why we can get a very interesting backarc basin here. Tonga subduction zone is characterized by its super fast convergence rate. In the northern part, the convergence rate could reach to around 24 centimeter per year. And even in the south, it's also very fast. It's like 16 centimeter per year. This is also part of the reason that the very fast subducting slab could cause a very active mantle convection, so that the mantle wedge is also super hot. Basically, this is very interesting. Because there are like different convergence rates from the north to south, we get super complicated backarc spreading center system. We will talk about it in the next slides. But basically, before we talk about the backarc spreading center, we want to talk about how they are formed. Essentially, they're formed by the melting of the materials, then the materials would rise up and form the new crust. The melting mechanisms are consisting of 3 different end members: flux melting, decompression melting, and high temperature melting. Usually, flux melting and decompression melting are 2 end members, and high temperature melting would be combined with these 2. The right 2 figures are from previous geophysical observations. The first one is a cross-section of velocity tomography, and the second one is the same cross-section with attenuation tomography results. Basically, the reddish color in the velocity means this is a low velocity structure, which could tell us this is high temperature or fluid or partial melting. Similar for attenuation, but the reddish color would mean high attenuation. So the previous studies could always suggest us with a very cold slab and a very super hot mantle wedge in the backarc. And also, if we look at the reddish region of both figures, we can see the reddish color is not a perfect round shape. It's also like extending to the east. So we think that there is an extending melt region in the Tonga area. So as I talk about the complicated backarc spreading center system, there are 3 different spreading center in the backarc. The left figure is a map view of Tonga subduction zone. The purple line here is the Tonga Trench, where the Pacific plate subducting beneath the Australian plate. The arc is like right here near the Tonga Ridge. The three spreading centers from the north to south is called Central Lau Spreading Center, East Lau Spreading Center, and Valufa Ridge. They're kind of parallel to the trench, but they do have different distances to the trench. If we start from the southmost Valufa Ridge, this is like closest to the Tonga Trench. If you think of the cross section, we get slab dehydration from the subduction slab. So Valufa Ridge could absolutely enjoy the most water input. So here, Valufa Ridge is like more like an arc. It's dominated by flux melting, which has a lot of water. If we take a look at the other one, the northmost Central Lau Spreading Center, this is like far away from the Tonga Trench, getting the least water supply from the slab dehydration. So here it's dominated by decompression melting. This is more like mid-ocean ridge. Think about mid-ocean ridge. Everything, you get a little, how to say, a wand on the surface, and because of the wand, this is like a weak zone. So pressure, the difference between the pressure on the surface and inside of the earth would force the magma, force the materia in the mantle to rise up. So again, Central Lau Spreading Center in the very north is dominated by decompression melting. And also for East Lau Spreading Center, which is in the middle, this is more like in the middle between the two end members. Again, we are talking about the two end members, but they are also greatly influenced by the high temperature. We will talk about the high temperature in the end. So the melting mechanisms are so complicated. We do want to use some technique to image the inside of the Earth to try to provide more evidence. This is when we want to utilize seismic attenuation. The left figure is a typical seismic signal. This is like what we can see from the seismic stations. For velocity studies, people only wants to know when the P wave arrives first. Basically, you know how far away the station is from the event, and you know when it arrives, we can calculate how fast the P wave is traveling. But for attenuation, we also want to talk about the energy containing in the wave field. The right figure, this is like not a real seismic signal, but this is like showing us how the seismic wave are attenuating. People want to use the letter Q to work as a quality factor to measure how much energy are being dissipated during a cycle. Like, one up and down is one cycle for a wave. So yeah, this is definitely much more complicated because we want to dive deep into the information containing in the seismic signals. From previous lab experiments, we can obtain some formulas that directly characterize the relationship between attenuation and grain sizes, temperature, and pressure, and some other parameters. So this is like super useful. And thank you all for the lab experiments. We can't invert for a very accurate attenuation without those experiments. And as I said before, velocity is kind of easier to study than attenuation because we want to know about how the energy are dissipating. But why do we still want to study attenuation? The first answer is we can use attenuation to accurately characterize the brittle and ductile behaviors of the mantle materials. Also, if you recall the two figures of the Tonga subduction zone here, both reddish areas could suggest high temperature, probably high melt content, but they have different sensitivities to the characteristics. This is like we are solving for a set of equations that have multiple different unknown parameters. By knowing more, by getting more observations, by giving more equations, we can solve for the unknown parameters better. So by combining both attenuation and velocity and combining with previous lab experiments and utilizing the terrific variable band rheology calculator, we are actually able to accurately quantify the melt porosity and also the temperature of the study area. So, given the information above, we really want to know about the attenuation structure here in Tonga. One of the reasons is Tonga mantle wedge is presumably the highest temperature. It could be the hottest mantle wedge on the Earth. So it's like constraining the end member on the Earth. We do have previous attenuation study here, but there are still teeny tiny differences inconsistencies we want to solve for. We are pretty confident about velocity tomography at this moment, which is at the left panel. Again, the reddish area means probably high temperature, high melt content. On the right, this is previous attenuation tomography results. If we look at arrow 1, this is the first inconsistency we observe for now. It's like we have weak velocity anomaly in the south, but we still have a very strong attenuation anomaly in the south here. And for arrow 2, there should be a volcano here. We do observe some anomaly here in the velocity, but we can't see the anomaly in attenuation. We are not saying that because the previous attenuation tomography is wrong, but again, as attenuation study is more complicated to conduct, we do want to use another different method to confirm that the inconsistency is right. Whether the inconsistency is real or not, this would be really valuable because we could feel safe to utilize both information to get to the final results, like the water content, melt content of the Tonga subduction zone. Again, if we get a cross section based on the line on the left panel, this is if we cut cross section from the 3 different spreading centers, this is the results on the vertical view. From velocity, we can definitely observe the strongest anomaly is in the north, the first panel. But for attenuation, previous attenuation study, we get exactly the same cross section as the velocity does, but the strongest attenuation now here is like appearing in the south. Again, we just want to confirm whether this phenomenon is right or wrong. If this really is, we can feel confident to calculate the melt porosity here. And we can contribute more to the melting mechanisms of the 3 different spreading centers. as I said just now, we want to know about the melt porosity. This is a figure from another paper from Jeff Ebers. They are comparing the attenuation models with the observed attenuation. The lines are the models from lab experiments or the other like empirical derivations. The circles here are real observation from attenuation study. The previous models you want to use is the thickest greenish line here in the bottom, which suggests 4% of melt porosity at most. However, based on this previous attenuation results, we are actually moving the yellow observation downward a little bit. This is also requiring us to move the thick green line downward a little bit again, which might require more melt porosity. This would driving the geochemists mad. This is why we really want to double confirm whether this is a true observation. Coming to the methodology part, I want to talk about the overview of the two steps. In the middle, this is a regular seismic signal we observe. On the top left panel, this is a very, very schematic figure of an earthquake and a station. The dashed line is the repath. So basically, the signal we recorded here is consisting of three different components. One is from the red star, the source. One is really the path, the dashed line, and another one is the site. The site itself also has some influence on the recorded signal. It's always very easy to remove the site, but we still want to decompose the source and path information to really get the pure path information to invert for both attenuation structure and also velocity structure. To get to our final attenuation structure, we first want to decompose the source and site, get a pure path term. Then we use a path to invert for a path average T star. This is our first step to get the attenuation result. Then for the second step, we combine it with velocity structure and use either linear inversion or nonlinear inversion to get the final 3D attenuation structure, like solving for the attenuation structure pixel by pixel. Again, I'm like repeating once and once again, we are revisiting the attenuation in the Tonga-Lau subduction system. The first question we want to solve for is an accurate melt porosity estimation. The second one is we want to solve for the inconsistency between the observed velocity and attenuation observation to get a right melt distribution in the three different areas. Because like this is a very complicated study region. We really want to know much more about it. And also, Tonga is a very unique place that has a lot of deep earthquakes. This is providing us with a very good chance to learn about the attenuation structure in the mantle transition zone. Again, the first step is to get the T-star inversion, which is like the path average attenuation. With a more accurate T-star inversion, we can get more accurate attenuation values, which could solve for the first and the second question. And then if we get the great velocity structure, we can absolutely obtain a better attenuation image of the study area. So we can also know better about the maldistribution. And finally, with a better attenuation tomography results in the Tonga region, we can solve for everything. And plus, we probably could see the features in the Mantle transition zone. Before that, I want to quickly talk about Tonga. The background of the background of my video is taken in Tonga. This is like the flowing hole and in the Tonga nearby ocean. I think this is like unique there. You can hear the wind howling and entering the flowing hole and generating the water here in my background. I really like it. I love Tonga. We utilize the data with 743 earthquakes in this area. And we only want to use the events that are deeper than 50 kilometers. This is another concept, scattering attenuation. Because for events shallower than 50 kilometers, the energy of them are dissipating anyway in the crust. Because in the shallow part, we get a lot of little tiny cracks. They are generating, they are really attenuating our seismic signal, but this is fake. Let's say the energy are not losing by like friction or some other thing, but P wave energy could probably transfer to S wave energy, and S wave energy could also come to P wave energy. This is like making everything messy. This is called scattering attenuation. This is what we can't solve for now. So we just like discard them. We definitely want to revisit them once we have the technique. That's too much. Anyway, coming back, we have a lot of very deep earthquakes. This is like the deepest one here we have in this catalog is reaching 677 kilometers. The stations we're using are mostly ocean bottom seismometers, and we have a lot of temporary land stations. I think that should be 17 temporary land stations. During this 1 year from 2009 and 2010, we actually recorded more than 1,000 events. But for this like 700 events, we can better solve for the source parameters. That's why we only utilize this much. Anyway, the first step, T-star inversion. It's like related to the reason I talked about just now. With better, we are revisiting the first step because we are only using 700 events that contains better source parameter data set, and then we can calculate a better path average T-star. What is T-star? This is like mirroring how the energy are dissipating along the reap path. We can also calculate the attenuation in this little string. It's somehow meaningful, but we can't get a 3D attenuation structure. But we are starting from here, from the left panel, the time domain seismic signal. This is what we record from the seismic stations. We choose a 5 seconds time window. And the 5 seconds time window of the P wave is the signal we want to study, and the left noise window is what we want to remove from the P wave signal window. Once we turn the signal from time domain to frequency domain, then here's the right panel. The blue line here is the real signal, and the reddish curve here is the noise signal. We are not trying to use a P-wave signal to reduce the noise signal, but we want to find a frequency band that we get pretty good signal to noise ratio. So the two green bars here could give us the range that this kind of data are really usable. So by fitting the blue curve inside the green bars, we are comparing it with a previous equation and invert for the T-star value here. This is only for one station event pair. As we said, we have like more than 60 stations and we have more than 700 events. So we are having a lot of repasses. By pretending that the quality factor, which represents the attenuation, we utilize the T-star to convert it to Q, the quality factor of the material. This is our results of the first step. The black dots here in the middle are the seismicities according to Benioff zone. This is like the geometry of the subducting slab. And on the top, the black triangles are the seismic stations that recording the signals. We got tons of messy lines. Each line is like connecting the station to the seismicity. It's like each line is obtained by one of this figure. So basically we have a unique T-star value for each line. And by calculating the path average 1/Q based on this, we can obtain this messy figure. Basically, the more reddish the color is, the higher attenuation it represents. Again, with higher attenuation, we probably could refer it to high temperature or high melt content. If we only plot those high attenuation rates with probably the 1/Q, 10/Q, 1,000/Q larger than 13-ish, we can very clearly see that there are high attenuation in the backarc basin. So yeah, this is the first step. We are confirming a kind of common sense that we should observe high attenuation in the backarc basin. So by utilizing this signal, we want to combine it with a great velocity structure to invert for a 3D attenuation structure. This is a revolutionary method we are using for now, and thank Joe again. So basically, we start from a totally random model. It's like the shape, the number, the values of the model are like always random. You can start with like a whole bluish color model, and then we perturb the current model by like adding the cell, removing the cell, changing the color, or change the location of this cell to get a new model. Whenever we get a new model, we can calculate the predicted T-star, which is like we can calculate based on the random model, we can calculate the color for these lines. By comparing the colors we calculated with this, we can call them as reference answers. If the predicted T-star are very close to our reference answers, we will think, oh, this current model is good enough. If they're not, we are still like updating them, perturbing them, and evaluating them again and again. This is one chain. We basically have to have more than 50 chains to conduct everything. In each chain, we're currently utilizing more than 1 million iterations and saving for around 5,000 good models. The right figure is one of the good model we think it is. Again, from the geometry of this lab, we can observe a high attenuation in the backcrack. And presumably, in the end, we can have tons of good models like the right, and all of them could represent the final results. There is a saying that all models are wrong, but some are right. This is also the case here. We are combining a lot of good models like the red figure to calculate the mean value to represent the final result. And also we can give a very good uncertainty map based on the large number of the good models. I should say there are a lot of pros of this method. The first one is we are utilizing the Voronoi diagram to parameterize the model. If we look at the both figures, the left one is what we are using for this method. The right one will be a regular grid for a linear inversion. Both are representing similar results, but we definitely have less grid here in the left and more grid in the right. Also, we should say it's very obvious that we get a lot of ray paths in the backcrack. So we can absolutely see that there are much more cells with less size in the left, but everything identical on the right. So we think this new parameterization is more data-driven and it should be more efficient because we are spending all the time the computer resources in the right place where we have a lot of recoverages. Then we also want to say about this method, because we are utilizing a huge set of good models, we can easily give a uncertainty map. You can feel confident to say, oh, the attenuation here is some value plus minus some other value. We can give a confident range based on some criteria. And also, as I said before, we are starting from a totally random model. So there is definitely no dependence on an input attenuation model, which is not the case for linear inversion. Also, because for Euro-linear inversion, they are requiring a confident input attenuation model at the first. The previous study only utilized the input model from 0 to 300 kilometer steps. So their confident attenuation results are also like constrained in between 0 and 300 kilometers. But this is not the case for MCMC. We can definitely have larger model space as long as we have data coverages here. Also, for the current code, I've been spending more than 2 years on this set of code. I'm confident to say that this is accessible and easy to run. We can invert it in spherical coordinate system. This is super valuable if you are inverting for an attenuation structure in a high latitude place. Also, we can manually add a low attenuation lid for the lithosphere, which is a common sense, but because of the lack of understanding of scattering attenuation in the lithosphere, we are not able to resolve it. So if you feel confident, you can just like basically mark the lithosphere as a low attenuation lid. Anyway, I added a lot of functions to this code, and I hope I can publish this paper with the code on GitHub in the following month. And I'm happy to talk about the details with you later. And yeah, also last month I went to Monte Carlo City in Monaco to like to say, please help me go through everything here, and it worked. Now the codes are like relatively fast with 20,000 repaths and 1 million iterations for each chain. If we are like running more than 10 chains each time, the inversion only takes less than 2 weeks. This is like, for me, it's a substantial improvement. And also since 2024, I've already used 420,000 CPU hours, but I started in 2022. I think the CPU hours have already like, at least it has doubled. Anyway, I'm trying to sell it. Please accept my advertisements. So now I'm going to show the preliminary results at first. This is also a cross-section in the middle. This is like in the East-Loss Writing Center. Again, we can see the high attenuation results in the back arc. The white circles are denoting the subtracting slabs. We can see a more constrained high attenuation region here in the back arc. And also, we probably are seeing a high attenuation structure in the Mantle transition zone. We can talk about it, but again, this is preliminary results. We are trying to update every input models, so I can't guarantee that this is the final results. If we take a look at the map view of all the studies. The first one is the attenuation tomography results we get from this study. The second one is the attenuation results we get from previous study, and the third one is the velocity. Because we're kind of like having more belief in velocity study, we really want to say, for the first one, for the first figure, it's like more consistent with the velocity. We're saying like, oh, this is better. I don't know. Everything should be confirmed after I update every input model and generate the newest data set. But at least for now, for arrow 1, we do see the weak attenuation in the south. For arrow 2, we do see high attenuation anomaly beneath the volcano. Again, the first figure is better, is consistent with the velocity. We probably will say the new attenuation map is better than the second one. If we take a look at the cross-section for the 3 different writing centers, again, if we only look at the rightmost panel, we get the strongest attenuation in the north. For the previous attenuation study, we get the highest anomaly in the south, but in the current results, we're observing the highest attenuation anomaly in the middle. I can't say which one is right, which one is wrong. Again, we tend to believe the velocity structure, and I do have a lot of confidence in my current attenuation codes. I will show the newest results after we update everything. So yeah. The first very important improvement we are going to do is to use a high resolution 3D velocity model. We are utilizing different velocity models like a 2D velocity model from Connor and Wings. And also we utilize the UUP07. It's like a global velocity structure model. By utilizing different velocity models, we are our conclusion is that attenuation results are highly dependent on the input velocity model. So we absolutely want to wait for a more accurate velocity structure to get the final results. And our anticipated results are like the final one, the model set 4. We should update the T-star data set with a better 3D velocity model, and then run it with MCMC to get the final results. What I showed just now is a updated T-star data set with the only 2D velocity model. So yeah. Once we get the final results, we can have a lot of confidence in estimating the melt porosity, but we already did it with the current data set, like the not very accurate results. We are combining the results from velocity and the current attenuation to calculate the melt porosity. The very broadband rheology calculator offers us the opportunity to calculate the melt porosity and temperature. So this is a figure. The x-axis of 1 and 2 and 3 are 3 different spots from the 3 different spreading centers from the north to south. If we only look the first one, the x-axis is melt fraction, y-axis is temperature. The color here means each dot on the figure is the melt fraction and temperature pair. The color here represents the possibility of this parameter pair. Let's see, the most yellowish color here means with around 7% of melt and around 1,400 degrees temperature has a very huge possibility of being the right answer. So we can kind of get a high possibility pair of the 2 parameters. And then luckily we get another independent constraints of temperature from geochemistry. So we are setting the y-axis as a constant value. This is when we can feel confident to give the value of melt fraction here. So based on the preliminary results, we are observing around 6.5% of melt in the very north in the central loss running center and around 2% of melt in the very south. This is kind of interesting to me because in the very north, we get the least water supply, but we get the highest melt porosity. One of the explanation I can have is it's also temperature dominated melting mechanisms because we get the highest temperature here in the north. So we can get a very high melt porosity here in the north. But again, once we get the newest results, we can constrain the melt porosity very well. And finally, we will definitely constrain the attenuation structure in the mantle transition zone. Again, use the preliminary results. We are observing a slightly high attenuation only here. It's like a relatively small region with a size of around 100 kilometers. I dare not to explain it, so I will put it in my heart. So yeah, with the modified technique, we can better constrain the attenuation tomography in the Tonga, and also by combining the velocity and the attenuation results, we can have a good estimation of the temperature and melt porosity. Currently, we are observing the high melt porosity in the north, although there are lack of water, the temperature is dominating the melting mechanisms here. And we probably would have regional high attenuation structure in the mantle transition zone. Still have to double confirm it. And finally, we will definitely reproduce everything with a very confident 3D velocity structure. So yeah, thank you so much for tolerating this very technical presentation. And yeah, thank you for all being my committee member. Thank all of my lab mates to giving me a lot of useful advices. That should be what I have for now.
So, all right. Thank you very much, Yurong, for the excellent talk. So next, we'd like to open for any questions you may have for Yurong. Please type your question in the chat. Actually, we already have one question for you, Yurong. The first question is from Sun Tianhao Zhe. The question is water content also playing a role? Could some of the inconsistency between the QP and VS distributions be caused by their different sensitivities to melt content, water content, and temperature?
Thank you. This is a very good question. Everything should play in a very important role. Specifically for water, we probably are sure that water could influence the observed velocity, but the influence of water on attenuation is always under debate. Somebody said that water content could act as somehow like melt to cause a high attenuation. Somebody said probably that's the oxidation state of water causing the high attenuation. So we don't know whether water would influence the attenuation. But anyway, attenuation and velocity are definitely having different sensitivities to water and also similar to melt and temperature. Especially for melt and temperature, lab experiments have already given us a lot of clear instructions of the different dependencies, which is really good. So again, if we do have the final results with the confident result numbers of velocity and attenuation, we would definitely want to know about how much how many portions that the velocity and attenuation are contributing to everything. Yeah.
All right. Thanks for your answer. Maybe I can ask a follow-up question to Sun Tianhao's question. Do you expect there some water in some regions of your study? Some part of your study regions?
I do, especially in a very, if we only talk about the Mantle Wedge on the very shallow part, in a very south region, because the spreading center are very close to the subducting slab, they should have more water from the subducting slab. We are expecting to see more water content in the Volufer Ridge. And this is not very safe to say, but from one paper I read before, they are attributing the high attenuation from mantle transition zone to the existence of water. There are also probable dehydration from the hydrous mineral in the mantle transition zone.
Thanks. I think people are still preparing the questions. Before that, I also have some questions for you. So first of all, question is about some details about measuring T-star. So to measure T-star, you need corner frequency. I know it seems you input some known corner frequency measured by previous studies. But problem is measuring corner frequency is affected by attenuation. So how do you think about this trade-off?
It is. I am lucky to talk with the people who is conducting the stress drop, the corner frequency research in Tonga. It seems that they are giving a rough estimation of the attenuation in the Tonga region, and also they are already doing very good. They did a 2-segment. They used 2 different values to represent different attenuation states in Tonga. This is also already good enough in the study area. So yeah, if you do have a lot of computational resources, we definitely want to the first choice is to invert both corner frequency and the attenuation together. The second is you are doing these 2 studies iteratively. But actually, if we are setting a very unrealistic, let's say, if we are setting a very high attenuation when we are calculating the corner frequency, once we input this corner frequency to the attenuation study, this could have like a reversed effect, which could result in a smaller attenuation. So basically, they have to converge. If you are assuming a very huge attenuation when you're calculating corner frequency, you would definitely get a smaller attenuation than you assume, vice versa. So yeah, this is not a very big problem for now.
I see. Thank you.
Thank you.
Yeah, I'm also interested in your MCMC method. It's amazing, I would say.
Thank you.
Especially are able to calculate the uncertainty map. So my question is, how reliable is the uncertainty map? Maybe the question is, what's the uncertainty of the uncertainty? So do you have any thought to do any test to validate the reliability of the uncertainty as it is?
The uncertainty is based on the mathematics we are using like in high school. If you see the contour here, the 2 here, this means the number here is like 10 minus plus 2. This uncertainty is standard deviation of every dot in among all the good models. So principally, we have to search for tons of good models. Like we have to obtain every good model, possible good model in the world, but we can't. The little teeny tiny uncertainty of the uncertainty might come from the limited models, but we can never reach to the unlimited model numbers. But anyway, I come back to this question. We are utilizing standard deviation, and I think this is the best estimation of uncertainty for now. This is the best technique we can have for now. This is like, it's not perfect, but it's tolerable.
Yes. Thank you. Actually, if my understanding is true, estimating uncertainty is affected by the regularization applied in the inversion. So my question is, do your inversion have the damping smoothing? And okay, so you don't have any damping and smoothing.
No, it's totally data driven and doesn't have any dependence on the input attenuation model.
I see.
They are trying to grow as much as they can. We are just like picking those models we like. This is like judging the models, but don't interfere with their growth.
Right. So let's see. Other questions from the audience. Maybe I can ask another question about how you parameterize your model space. You use Voronoi diagram. So is a total random, or you design the diagram based on the earthquake distribution?
Totally random. Like this is one of the starting model we get. Basically, we start from random number of cells, random location of the cells, and random values of the cells. They are totally random, but there do have some like prior distributions of this starting model. But anyway, we're not picking any starting model.
Sorry, but you still need to input a starting model, right? Yeah, right.
We don't have to. Like then now for this one, we have 5 stars. That means we have 5 Voronoi cells, but this is like randomly generating 5. And then we randomly assign the location of the 5 cells. We randomly assign the color for the cells.
I see. Thanks.
Thank you.
Yeah, my last question is a code written in fortune in MATLAB or in Python, you have tons of runs. It's, I can
Yeah.
imagine it's very time consuming. So I'm curious which language you use.
It is. So we are utilizing Julia. Julia is like as fast as Fortran runs, but it also contains some packages like Python. But for now, I think Julia is a best option we want to choose. It's fast.
Yeah, very cool. Yeah.
Thank you. We can talk about the other things privately.
Yeah.
And thank you for your time.
Yeah. So I did not see other questions in the chat. So if there's no if there's no more questions, let's thank Yurong again for today's excellent talk. And also don't forget to provide us some feedbacks about this webinar using the link I pasted in the chat. All right, so thanks everyone for your participation today, and see you next week. Goodbye everyone. Take care.
Bye. Thank you.
Bye.